What is up, Simpsonian Army? Back at it again with the Sim Science Saturday. Nothing I'd rather do than, cozy up on a rainy Saturday afternoon and work on balancing some equations. Okay? So, balancing equations. Some people love it, some people hate it. At the end of the day, it's like a puzzle that just takes some practice, and I think anybody can be very good at it. Okay? So, in class in general, a lot of you seem like you're getting it. You just got to balance out, make sure you got the same number of atoms on each side. But there were a couple things I saw in class on Friday that I want to go over, make sure you guys see. So this will be a little bit of an overview on that, and I'm planning on making another video going through all of the equations from the in-class activity, group activity from Friday. So first of all, one thing I saw you guys missing a lot are diatomics. So diatomics are atoms that exist in nature in pairs, and they do this so that they can achieve a shared octet of atoms that covalently bond to another atom of the same species in order to do that. So if we look at our periodic table, which I didn't erase from my first shooting of this video, if we look at our periodic table, there are 7 diatomics. Hydrogen up here, and then the other 6 are in the shape of a 7 over on this side of the periodic table, okay? So all 6 of these. So diatomics are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All right. So like I said in class, one way to remember that is Hofbrinkel, Hofbrinkel, or you could switch around and go Brinkelhoff. All right. So every one of these is going to exist in a pair of 2 in nature if it is alone. If it is alone. Okay? If they are in a molecule bonded with other atoms or a polyatomic or whatever it might be, they can exist in different numbers. Take nitrate, for example, NO3. Alone nitrogen would have 2. Alone oxygen would have 3. Okay? In its standard state. But in nitrate, nitrogen has 1, oxygen has 3. If they are alone, they exist in a pair of 2. If you see in an equation, oxygen combines with this or that, or nitrogen or iodine or bromine combines with this, whatever it might be, you know that you're going to be writing it as O2, N2, Br2, okay, diatomics. Those are diatomics. Another thing that I think you guys need to be made a little more aware of, again, are polyatomics. So we got an intro to these in the last section, talked about how they fit into names. So one key thing, if you're reading an equation and trying to write it out, you can identify polyatomics by the suffix "ite" or "ate." If you see the T, okay, it's a polyatomic. I don't know if that helps, but "ite" or "ate" versus "ide," IDE, which is just telling you that you have a negative anion of an element. Okay, but the "ite" or "ate" is telling you that it is a polyatomic. Now, we learned in the last section to treat polyatomics as single units when we're naming compounds because they each have their own charge, and when they have their own charge, you can balance that charge with whatever cation they're combining with. When you're balancing equations, you can treat them as a single unit. Treat as a single unit if they appear, or it appears unchanged on both sides. Okay, so if you have a polyatomic like sulfate SO4 and it's in a reaction with something else, okay, all right, let's say this is a single displacement, so you get YSO4. That's probably the worst Y in history of Ys. Okay, SO4. Now we can treat this sulfate as a single unit because it's unchanged on both sides. So if we're balancing it, we're going to get the same total of sulfurs and oxygens, whatever we do to it. If it broke up and you had sulfur and oxygen separately, you say it was sulfate over here, and then on the product side it broke up, you would have to treat sulfur and oxygen as individual atoms because they're not going to be in the same ratios after they're broken up. So it can be kind of hard to explain with words. Again, with practice, you start understanding this a little bit better. So let's look at a simple reaction that I chose to break this down. So when we're approaching a reaction written out in words, what are we looking for? Well, here we have nitrogen and oxygen. Okay, so there are two elements combined to form nitrate. Okay, so you should notice the ATE here, and we just talked about nitrate. ATE tells me this is a polyatomic, so I'm going to have to look that up on my polyatomic chart. Now, what else is this reaction telling me? Well, let's look at the other words. And, combine. Okay, either of these is telling you plus sign. All right, this could say nitrogen combines with would be plus. Nitrogen and oxygen. Nitrogen plus oxygen on the reactant side. All right, I saw some of you writing things out, combining them. Like for this, you would have written NO together, but when you see the and or combines, that's telling you they're separate things on the reactant side, and then they're combining to form. When you see something along the lines of to form, that's telling you that that's your arrow, that's your reaction arrow. So these, the reactants over here on this side on the left are coming together to form, they're reacting to form nitrate. Okay, so how would this be written out? Well, we have nitrogen, like I said, plus oxygen combining to form, they're reacting to form nitrate, which if you look on your polyatomic sheet, you'll see is NO3. Now, hopefully you noticed, and again, as you do a lot of these problems, it'll start to look weird to see just an N or just an O because they are diatomics. So if it says nitrogen, I know that means N2. If it says oxygen, I know that means O2. All right, combining to form nitrate. So what am I working with here? Well, I have a polyatomic on one side. All right, and you could picture this reaction, this is a synthesis reaction, two things coming together to form something new. If we're going the other direction, it'd be a decomposition, nitrate breaking into nitrogen and oxygen. But either way, I have a polyatomic on one side that does not appear on the other side. So I'm not treating this nitrate as a single unit because the nitrogen and oxygen aren't together on the other side. So I have to treat each atom individually. Now, this is a pretty simple reaction. Some of you might already be looking at it and know how to balance it, but let's do it the thorough way. So I have nitrogen and oxygen on one side, and I have nitrogen and oxygen on the other side. Again, I'm breaking up the nitrogen and oxygen on the product side as well because nitrate does not appear unchanged. So, all right, now we tell a number. So the subscript tells you how many of the atom in front of it you have. If it's a molecule, the subscript still only tells you the number of the atom in front of it. A coefficient, like we write in, tells you affects every atom in a molecule. But anyway, we have 2 nitrogens on this side and 2 oxygens on this side. Over here, this 3 is only telling me the oxygen. It's not telling me anything about the nitrogen. So I know I have 3 oxygens and just 1 nitrogen. All right, so now let's balance this. Whenever you see 2s and 3s, your best bet to start with is try and get stuff to 6. So I'll erase all these arrows and stuff, make it a little cleaner to balance. Okay, so I'm going to put a 2 out front here because I want to change my oxygens to 6 because this is a coefficient. It's affecting both things here. So I'm also going to be changing my nitrogen to 2. And to be clear, this oxygen turns to 6 because now I'm saying that I have NO3 and NO3. I have this twice, 2 nitrates. So that means it's like an addition problem. So I have 3 oxygens plus 3 oxygens is going to be 6 oxygens, and 2 nitrogens is going to be, or nitrogen plus nitrogens, 2 nitrogens. Okay, just to be clear. So I'm multiplying the coefficient by the subscript. All right, so now I need 6 oxygens over here. Well, I'll just toss a 3 in front of that. And now I have 3 times 2 oxygens, so this turns to 6. My nitrogens are already at 2, which matches the nitrogen on the other side. So this is my fully balanced equation, okay? I need N2 plus 3 O2s to get 2 molecules of nitrate, 2 nitrates, okay? So keep an eye out for the diatomics. Know that whenever you see the words hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine as a single unit alone in an equation, that's going to be exist in a pair of 2. Polyatomics with 8 or 8, you need to treat them as a single unit, or I should say you can treat them as a single unit if they appear on both sides. Breaking down the atoms into individual atoms will still work. It's just going to take you more time to balance it out. So, but if they break up as it did here, or it didn't break up but combined, either way you don't have nitrate on both sides, so you treat each atoms as individuals, and then you can balance your equations. Okay, so hopefully it gives you a strong foundation on what you're looking for, or at least two of the biggest problems I saw with balancing. But I will go into more detail on balancing as I go through the problems from the in-class work in my next video. Thank you guys for watching. Please smash that like button if you learned a little something new about chemistry today, and definitely subscribe, turn on your notifications. I think that these videos and this YouTube channel is the best tool I have to give you guys the most thorough explanations for things that I can and prepare you for your upcoming tests and helping you master chemistry. Thank you guys for watching. I'll see you in the next